Have you ever looked up at those giant metal towers marching across the landscape and wondered how they work? They're the backbone of our modern world, carrying the electrical energy that powers everything from our phones to our refrigerators. But here's something you might not know. There are two main ways to send that power over long distances, and they are in a constant, invisible competition. Most of the power lines you see zipping across fields and alongside highways are using something called high-voltage alternating current, or HVAC. It's the reliable go-to system for our regional power grids. It's what brings electricity to your neighborhood, a familiar and dependable workhorse. Now let's consider the alternative. High-voltage direct current, or HVDC. While HVAC is more common for shorter distances, HVDC is the heavyweight champion of long-distance power transmission. When we need to send massive amounts of electricity across entire continents or under vast oceans, HVDC is the technology we turn to. It's a bit like the difference between a local delivery truck and a massive cargo ship. The truck, or HVAC, is perfect for zipping around town, but the ship, HVDC, is what you need to move huge quantities of goods across the globe. HVDC is the unsung hero behind some of the world's most ambitious energy projects, quietly and efficiently moving power where it's needed most. One of the most obvious ways to tell these two systems apart is just by looking at the wires they use. If you peer up at a typical HVAC transmission tower, you'll almost always see conductors in groups of 3. This is because alternating current is generated and transmitted in 3 separate phases, each one slightly out of sync with the others. Think of it like 3 people pedaling a bicycle, each one pushing at a different time to keep the wheels turning smoothly. This 3-phase system is incredibly effective for generating and distributing power locally, which is why it became the standard for our electrical grid in the first place. HVDC, on the other hand, keeps things simpler. It only needs 2 conductors, one to carry the current out, a positive wire, and one to carry it back, a negative wire. Sometimes it can even use just one wire with the ground acting as the return path. This streamlined design immediately shows one of its key advantages for long-distance travel. Fewer wires mean you need narrower towers and less land, which can make a big difference when you're building a power line that stretches for thousands of kilometers. This physical simplicity is a clue to the deeper electrical efficiencies that make HVDC so special for epic journeys. So, if HVDC is so great, why isn't it used everywhere? The answer, as is often the case in engineering and science, comes down to economics. For shorter distances and at lower voltages, building an HVAC system is simply cheaper and less complicated. The equipment needed to generate, step up, and step down AC voltage is standard, widely available, and highly reliable. Our entire electrical infrastructure, from the power plant to the outlet in your wall, was built around AC. So, for sending power to the next town over, sticking with the tried-and-true HVAC system just makes financial sense. It gets the job done without any unnecessary bells and whistles. However, the economic equation flips entirely when you start talking about transmitting power over very long distances. A great example of this is the incredible Changji-Guquan UHVDC link in China. This technological marvel operates at an astounding 1,100 kilovolts and can transmit 12,000 megawatts of power, enough to supply a major city, over a distance of more than 3,000 kilometers. That's like sending power from Los Angeles to Chicago. For a project of this colossal scale, using HVAC would be impractical and wildly expensive due to the technical problems that crop up over such a long journey. HVDC becomes the superstar when the miles start piling up. This is because every transmission system has a break-even point. Imagine you're deciding between driving your car or taking a plane for a trip. For a short drive, the car is cheaper and easier. But for a cross-country journey, the cost and time spent driving becomes so high that flying is the better option. It's the same with HVAC and HVDC. HVAC lines have lower initial terminal costs, but higher power losses and management costs per kilometer. HVDC lines require very expensive converter stations at each end, but their transmission lines are cheaper and more efficient over distance. After a certain number of kilometers, typically around 600 to 800 kilometers for overhead lines, the savings from HVDC's efficiency outweigh the high initial cost of the converters. Ultimately, the choice between HVAC and HVDC is a classic engineering trade-off. For the vast network of lines that form our regional grids, HVAC is the undisputed king. It's cost-effective, easy to manage, and perfectly suited for the job of delivering power over moderate distances. But when we need to connect a remote hydroelectric dam in the mountains to a bustling city thousands of kilometers away, or link the power grids of two different countries, HVDC steps in. It's the specialist tool for the biggest jobs, enabling us to build a more connected and resilient global energy network by conquering the tyranny of distance. To really understand why HVDC is the preferred choice for long routes, we need to look at some of the invisible challenges that come with transmitting alternating current. Because AC electricity constantly changes direction, swinging back and forth 50 or 60 times per second, it creates fluctuating electric and magnetic fields around the wire. These fields can cause all sorts of mischief. One problem is called inductive and capacitive interference. The changing fields can actually induce a voltage in nearby objects, and the electric field can ionize the air around the conductor, causing a small amount of electricity to leak away into the ground, a constant and wasteful power loss. Another strange issue with long HVAC lines is known as the Ferranti effect. Because the long transmission line acts like a giant capacitor, it can cause the voltage at the receiving end of the line to become higher than the voltage that was sent in the first place. This might sound like free energy, but it's actually very dangerous and can damage the expensive substation equipment that's waiting to receive the power. To combat this, engineers have to install special equipment called shunt reactors along the line to absorb the excess reactive power and keep the voltage stable, adding to the overall cost and complexity of the system. But wait, there's more. The current doesn't even flow through the whole wire evenly. This phenomenon is called the skin effect. At the frequencies used for power transmission, the alternating current has a tendency to crowd onto the outer surface, or skin, of the conductor. This means the center of the wire carries very little current, which is an inefficient use of all that expensive copper or aluminum. While engineers use stranded conductors to help reduce this effect, it's an inherent inefficiency baked into AC transmission. It's like paying for a 4-lane highway but only being able to use the outer 2 lanes. These issues, interference, voltage instability, and the skin effect, all get worse as the transmission line gets longer. For a short line, they are manageable annoyances, but for a line stretching hundreds or thousands of kilometers, they add up to significant power losses and require costly countermeasures. This is the fundamental weakness of HVAC for long-distance transmission. The very nature of alternating current, which makes it so easy to generate and transform, becomes its own worst enemy when it has to travel a long way from home. So, how does HVDC magically avoid all these problems? It's all because direct current is steady and straightforward. With DC, the voltage is constant, and the current flows in only one direction. This means it creates a static magnetic field and a stable electric field. So, there's no inductive or capacitive interference with the surroundings. Furthermore, because the frequency is zero, the skin effect completely disappears. The current flows uniformly through the entire cross-section of the conductor, making the most efficient use of the material. It's a much calmer, more orderly way to move electrons, which results in lower power losses over long distances. Of course, there's a catch. Our power grids generate and use AC power, so to use HVDC for transmission, we need to perform a bit of electrical alchemy. This happens inside massive buildings called converter stations. At the sending end, high-voltage AC from the grid is fed into the station where powerful electronic switches, like thyristors or modern IGBTs, convert it into DC. The electricity then travels along the HVDC line. At the receiving end, another converter station, called an inverter station, does the exact opposite. It takes the high-voltage DC and converts it back into AC, ready to be integrated into the local grid and sent to consumers. These converter stations are the heart of any HVDC system, but they are also its most complex and expensive component. They are filled with transformers, filters to smooth out the electrical signal, and massive halls of power electronics, all requiring sophisticated control systems to operate. This high cost is the primary reason we don't see HVDC lines running to every neighborhood. The expense of building 2 of these giant stations is only justified when the savings from lower power losses over a very long distance are great enough to offset the initial investment. It's a significant upfront cost for a long-term gain in efficiency. In the end, both HVAC and HVDC are essential technologies for our electrified world. They aren't rivals, so much as partners with different specialties. HVAC remains the undisputed champion for regional power distribution, forming the dense web of our grid that keeps our communities running. Meanwhile, HVDC is the crucial link for our energy future, allowing us to tap into remote renewable resources, share power across continents, and build a more stable, efficient, and interconnected global power system. By understanding the strengths of both, we can continue to power our planet in smarter and more effective ways.